This video will cover the destructive test of a restrained light frame wood structure model. This test is the second part of a comparative study that will investigate the behavior of a light frame wood structure model with the roof harness retrofit system applied. The test setup shown here is for the displacement test of the retrofitted structure. This test uses an identical roof and model configuration to the one used in the unretrofitted displacement test, where this time a retrofit system is introduced to the roof. The retrofit is a reduced-scale version of the roof harness system developed by Ryan Jacklin under the supervision of Dr. Ashraf Eldamadi. Like the roof of the reduced-scale model, the components of the retrofit system have been specifically designed to emulate the behavior of the full-scale structure and retrofit system under similar wind loading conditions. This is done by reducing the cross-sectional area of the cables and spreader beams. Visible in the test setup is also the pitot tube, used to measure wind velocity, as well as the S-load cells connected to the retrofit system, which are used to monitor tension and measure applied pretension. Once again, this test will isolate toenail withdrawal at the windward roof-to-wall connections as the desired mode of failure. Displacement at these connections is continuously monitored as the wind velocity is increased over an applied range. Just as in the displacement test of the unretrofitted structure, distinct stages in the failure process will become apparent. However, due to the presence of the retrofit system, the wind velocity at which these events occur is importantly increased. Additionally, catastrophic failure by roof overturning about the leeward wall is entirely prevented by the presence of the retrofit system. Footage of the test begins where the fan speed is increased to approximately 20 meters per second and held constant for 30 seconds. At this point, the displacement at the roof-to-wall connections indicate that these locations have just achieved initial separation from the top plate, as the own weight of the roof plus the pretension force is resisting the applied uplift force due to suction. This represents a 5 meter per second increase in the velocity at which this failure stage occurs, as compared to the same event in the test of the unretrofitted structure, which is largely due to the presence of the pretensioning in the retrofit system. At approximately 30 meters per second, roof-to-wall connection 3 begins to experience significant withdrawal, followed shortly thereafter by roof-to-wall connection 2. Again, the lateral flexibility of the roof allocates uplift by tributary area, promoting early failure in these two interior connections. Though initial full withdrawal failure can be observed in this test, the benefit of the retrofit system is clear, as the wind velocity at which this event occurs is improved by approximately 8 meters per second as compared to the same event in the unretrofitted displacement test. This improvement is a combination of the effects of both the pretension as well as the load sharing between the retrofit system and the roof-to-wall connections. The mechanism of load sharing is engaged as the roof-to-wall connections begin to deflect. As the stiffness of the retrofit system is predominantly linear, while roof-to-wall connection stiffness is nonlinear, load transferred from the roof-to-wall connections to the retrofit system follows the decay in toenail stiffness. At the end of the video, the wind tunnel speed is sustained at 36 meters per second for 30 seconds. This is the highest wind speed the current wind tunnel configuration can produce, and, as is observed, only the interior windward roof-to-wall connections experience full withdrawal. Using finite element analysis models to predict the behavior of the structure and retrofit, the predicted wind speed at which all roof-to-wall connections would fail is determined to be 40.5 meters per second, an approximate 70% increase in wind speed compared to the unretrofitted structure. This would mean that a full-scale historically built light frame wood structure that would normally experience failure at wind speeds of 125 kilometers per hour would be able to withstand sustained wind velocities of approximately 215 kilometers per hour. At this point, as previously mentioned, though all roof-to-wall connections have achieved full withdrawal, the roof is prevented from overturning failure by the presence of the retrofit system.